Alright, so we move on to look at continuous functions and introductory analysis. Wow, very good. It's going to be interesting. So, in fact, this is not your first time hearing continuous functions. Or from your calculus 1, you learned something about continuous. You learned something about what? Continuous functions. And we said that we have 3 conditions for a function to be continuous. And I hope you remember those conditions. In the same way, if we let f of s be continuous at s naught, now this is the function f of s. When we let it be continuous at s naught, now here the point you are going to get here is s naught for s axis and L for y axis. But this L is the same as f of s naught because the value of if f is 2, when you replace it inside of the function f of s, then let's say it gives 5. That means that the 5 is the output. So the input is the s naught and the f of s naught is the what? The output. So L is the same as f of s naught is the same as L. Alright. So we are saying that the limit as s approaches s naught, definitely it will get to reach a certain value. So for this function to be continuous, 3 conditions involved. And the first condition is that s naught must be in the domain of f of s. S naught must be in the domain. But if it's not in the domain, then it's going to be asymptotic to be somewhere or whatever. Because we say that a function is said to be continuous if it has no asymptote, no breaks, or pole. So that is that. 2. The limit of f of s must exist. Must exist. And since if the first condition established, then you can attain the second one, because once it is in the domain, then it will exist. 3. The limit as s approaching s naught of the function of the s, that will be equal to that. Alright, so these are the 3 conditions. So when we are given a limit of any function where s approaches s naught and it's equal to this, yes, even if it's true, but we have to prove it. We have to prove it by stating the theory, and you cannot do away, or you cannot prove by doing away with the theory. You have to state the theory. So please always don't forget to state the theory. So that is that or that. For a continuous function, that is given epsilon positive, there exists delta being equal to delta in terms of epsilon, which is greater than 0, such that s minus s naught. Now, don't forget, this is not s minus a as we were previously doing. No, please don't forget that. Less than delta, then this is that. Very good. So, in the first place, in our previous video, we were replacing the f of s naught to be constant, but here we don't do it as such. Now, let's try our first question. State the definition of continuous and uniform continuity of a function f, and prove that f of s is equal to s squared is continuous on R, but not uniformly on R. But before we attack our first question, then we have to understand what this uniformly continuous means. Alright, so from this, let's go to continuity in an interval. Continuity in an interval. Alright. I mistake. I nearly forgot it. That is why I was about to go with the question. So let's go with continuity in an interval. And if continuity in an interval is the same as uniform continuous or uniformly continuous. So this uniform continuity. Uniform continuity. So we state the theory. If f of x is within an interval, then we state, given any positive epsilon, there exists delta being equal to delta in terms of epsilon, which is greater than 0, such that belonging to the interval. In the same approach, somehow similar to what we have here, wherever alright, so that is for uniform continuum. So now let's come back to the question. State the definition, right? I would like you to. Hope you are done with this part. Okay, now right. State the definition of continuity and uniform continuity of a function f. And prove that f of x is equal to s squared is continuous on R. Is continuous on R. But not uniformly continuous on R. But not uniformly continuous on R. So we'll be doing using it to prove that f of x is equal to s squared. But before that, let's state. We are going to state that for continuous and that for uniformly continuous. So, in case you're in an exam, this is what you are supposed to write. So definition. Continuous element. So the first one, a function Alright. Alright. So these are the two conditions. This is for examination. Alright. So anytime you are asked to state it, state the definition of continuity and uniformly continuity. Continuity and uniformly continuity of a function f. And prove that, for that one, it depends on the question. It's continuous on R, but not uniformly continuous on R. So that's what you did. That's the first one. The first one is a function of f is said to be continuous on R at s naught. When the limit at s approaching to s naught being equal to that, then you choose the equivalent statement. If given any positive epsilon, there exists delta that such that wherever. So this is if it's possible to find out that s naught is depending on delta, then the function is said to be continuous. So that is for the first part. Secondly, a function f of x is said to be uniformly continuous. Uniformly continuous on R at s naught. Then the limit at s approaching s naught of f of x is equal to 8. If given any positive epsilon, there exists delta in terms of epsilon greater than 0, such that s minus s naught less than epsilon, wherever this is of that. That is, if it's possible to find s naught independent. Don't forget this is what? Dependent. But this is what? Independent on delta. Then we say f of x is uniformly continuous. Very good. So let us now use it to prove. Let us now use it to prove that f of x is equal to s squared. It can be anything. It can be f of x is equal to s squared minus 1 or that or that or that. Oh, very good. So we are going to use it to solve about 2 questions. Then we end there for that. Then we end there for that. So we look at our first question. We are going to use it to prove that f of x is equal to x squared. Very good. Now, don't forget that we start with this f of x minus f of s naught. Alright? And what is f of s naught? This is f of s naught, the output, and this is the what? The input. Very good. So, the f of x is equal to this, but f of s naught will be equal to s squared naught. If they are not the same, this is not the same as this. So here we get s squared minus s squared naught. Alright. And this is difference of two squares. So here we get s minus s naught s plus s naught. Very good. So we write this as so we write this as now we have here to be s minus s naught. So with this, we can manipulate it so that we can get something also like s minus in it. Okay. So for us to get s minus in it, we have to do and undo. All right. So we break. So we bring x, but we are not going to bring plus s naught, but rather minus s naught. Okay. Then to do, then you will do s naught before we bring this plus s naught. Hope you can see that. This is 0. So s minus s naught. Then here we can get this inside of a bracket. Okay, so here we get s minus s naught, then plus 2 s naught. Very good. So from inequality, that is triangle of inequality. So from triangle of inequality, all right, from our triangle of inequality, we know that s minus s naught this is going to be equal to s minus s naught, okay, plus 2 s naught. Alright, so this is going to be the same as this. Let me check. No, there is nothing here. So this is going to be s minus s naught. Okay, very good. So we get s minus s naught here, s minus s naught here, and plus 2 s naught. So from our triangle of inequality, you can write this as this. So here we choose, since we have 2s minus s naught, it's like x minus a. So we elect here to be delta 1 or delta 2. Then here will be delta 1 plus 2s naught. I hope you are familiar with it. Very good. So we can choose. You know that here we choose delta 1 to be 1. So that we get delta 2, 1 plus 2 s naught. Then we choose delta 2 to be equal to, if you can see it well, it's going to be epsilon over 1 plus 2 s naught. You can equate everything here to be epsilon and see what you're going to get. So you're going to get epsilon over 1 plus 2 s naught multiplied by 1 plus 2 s naught. This cancel this, then we get epsilon. That is that for that. So we have been able to prove that that is equal to this. Very good. Now let's look at our second example. Okay, so here we can now conclude We can now conclude that now. So let's conclude. Now, since let me write. We can now conclude that since our selecting of delta in terms of epsilon, let me write it for delta in terms of epsilon, it's depending on S naught. Then is continuous, but not uniformly continuous on R. So this is going to be our conclusion. That since our selection of delta, which is in terms of epsilon, what we can see that delta is in terms of epsilon, is depending on S naught. Therefore, we can say that this is equal to this is continuous on R, but not uniformly continuous on R. Don't forget that anytime that when you select two deltas, I'm talking of the continuous function. When you select two deltas, that is telling you that it is dependent. For the independent, you get only one delta. So your conclusion should affirm it well. All right. Let me see if I can get one more question for us to solve. Here we have to show that this is equal to this. It's uniformly continuous on R. Now, after solving this question, I'll explain something to you for you to get these things straightforward. In fact, the moment you see the function given in the question, you have to know that is it going to be dependent or independent so that you can know how to conclude it well. So you let S not to belong to all real numbers. Then the limit of this at S approaching S not is equal to that means that wherever you see this is supposed to be, let me state that one before. It's the same thing, you can do it that way or this. Given then you show an equivalent statement, given any positive s from there and then delta, set that very good. So this is what we mean. So what is S naught? That means that in the f of s, wherever you see s, put what the S naught. So here you get f of s is 3s plus 7 minus 3s naught plus 7. And that is fs naught. So here we get 3s plus 7 minus 3s naught minus 7. Very good. So, looking at what we have now, we can see that this will clear out this. So we get 3s minus 3s naught. And don't forget what we want to achieve. Don't forget what we want to achieve. So we factor out less than delta. So we factor out, so we can factor out 3 here, we get s minus s naught. So that means that we have been able to achieve that. Very good. So this is going to be, so this is going to be 3. Then replace the s minus s naught by delta. So here you see here, like unlike the previous one, it was 2 deltas. Here it's only 1 delta. Why? I will tell you. So here we choose delta to be equal to, we choose delta so that it will clear up this. So delta will be equal to epsilon over 3. So it's going to be less than or equal to 3 times epsilon over 3, so that the 3 will cancel out. Then we are going to get this to be equal to less than or equal to epsilon. Alright, so that means that we will be able to prove that this is uniformly continuous on R. So this is going to be your conclusion. Your conclusion is going to be the same as the first one, but here, instead of writing dependent, here you are going to write independent. The reason is that here we choose only one delta. Unlike the previous one, it was delta 1 and delta 2. So always don't forget that. From the first question, it was f of x to be equal to s squared. That is quadratic. That is why we had delta 1 and so that is why we had delta 1 and delta 2. Delta 1 and delta 2 because it was quadratic equation. So anytime you are dealing with a quadratic equation, be expecting to get it to be dependent because of the delta 1 and delta 2. But looking at what we had here, this is a linear equation. So if it's a linear equation, you are going to get only one delta. You're going to get only, or you're going to choose for only one delta. And for that matter, it's going to be independent on delta. But when you choose two deltas, it's going to be dependent on what? Delta. That is why we concluded on the first one that is dependent on what? S naught. But here, the conclusion is going to be since our selection of delta in terms of S naught is independent on S naught. F of x is equal to 3x plus 7 is uniformly continuous, not like the previous one. That one is continuous, but it is uniformly continuous on R, not but not continuous. Alright, so that is how you are going to do it. So if the function is linear, you get one delta, which is going to be independent. But if it is quadratic, you get two delta, which is going to be dependent. Alright, make sure you keep on solving more questions and see you for the next video. Alright, let me add this question to you as bonus. Okay, so you start by quoting the theory if given any possible slot like that. Alright, so straightforward. We know it's going to be f of s minus l. Alright, so here we get 2 over square root of s minus 2 over square root of a. So what is the LCM? You first ask yourself of the LCM. And the LCM is going to be square root of ax. So the 2 multiply square root of a, then these 2 multiply the square root of x. Okay, so when you get 2 square root of a over minus 2 square root of x, all this over square root of ax. Alright, then you rationalize it. You need to rationalize this part. I want to be quickly move fast on this because it's a bonus. You need to rationalize this. And when you rationalize the numerator. So you get 2 square root of a plus 2 square root of x over 2 square root of a plus 2 square root of x. So this you get 2 square root of a squared, 2 square root of x squared over here the square root of a s will multiply 2 square root of a plus 2 square root of x. Very good. So here this is 4a minus 4x. All this over. Then when you multiply this by this, you're going to get 2a square root of s plus 2s square root of a. Very good. Now, this is going to be by analysis. It needs to be less than. You need to bring this an absolute sign, alright? So we want this to be here because we want to get something like s minus a. So here we get 4s minus 4a over 2. Here we can factor 2 out. So we get a square root of s plus s square root of a. Very good. Very good. So when we factor 4 out here, we get 4s minus a over, then here 2, the 2 can come out. Then we get a square root of s plus s square root of a. Very good. And this is the same as 2 out s minus a over square root of a square root of s. Hope you are following. This goes to this 2. So a square root of s plus s square root of a. Alright, so you see we have been able to achieve s minus a. So we can replace that by delta over a square root of s plus s square root of a. Very good. Very good. Now, here you have to be careful. Here you have to let s equals 1 because we don't choose from here, we have to choose delta, but we don't choose delta to be in terms of x. Please take note, we don't choose delta to be in terms of a function. So what we have to do here is that we have to replace x by 1. So we get 2 delta over a square root of 1 plus 1 square root of a. So this is going to be 2 delta over a plus square root of a. Hope you can see that. Very good. Then you choose. So here we choose epsilon to be equal, we choose delta to be equal to, as I said, you can equate the whole this by epsilon and make delta the subject. So doing that straight away, delta will be equal to a plus square root of a over 2 epsilon. Alright, so by substitution, by substitution, you're going to get 2 multiplying a plus square root of a over 2 epsilon, and it's going to be all these over a plus square root of a. So let's multiply by 1 over a plus square root of a. This cancel this, and this will cancel this. So we are going to be left with less than what? Epsilon. Alright, so that's going to be the final answer for that. So you can set to be equal to any value. It's not that you can let it be equal to 1. You can let it be equal to any value, okay? But we don't choose delta to be included with f7. Alright, you can see how to type. See you in the next video. Please do one more thing for me. Subscribe. If you don't subscribe, you are not helping us. Make sure you subscribe so that we reach out with a lot of people with the beauty of mathematics, and also share it also and invite your friends in other universities to also enjoy it. Thank you very much.